All right, let's talk buoyancy force. And where does buoyancy force come from? Well, there's our object that's suspended in the water, and in this case the object is not moving, it's not going up, it's not going down, it's not going sideways, it's just suspended in the fluid, so it has neutral buoyancy is what we would say. Well, what forces are acting on this object? Well, we have the force of the water above the object, and we have the force of the water below the object. Remember, these forces are a result of the pressure of the fluid pushing on the object in all directions. Pressure is pushing on the object in all directions. A couple things we need to know just as we work through this, determining buoyancy force. We need to know the height of the water above the object and the height of the water below the object. All right? That's going to help us determine the buoyancy force. Now, I'm only going to consider these two forces, but remember, pressure is acting on this object in all directions. Ultimately, we're going to be calculating a net pressure and a net force. That net force will be the buoyancy force. But I'm going to use two forces to get us there. Right? So this is our schematic. We may come back to it. Let's look at some equations. We know that the pressure pushing down on the object is a function of the force of the weight of the water pushing down on the object and the area of the object, or really the area of the rectangle sitting above the object. All right, that's the weight of the fluid. Weight of fluid. Oops. Yeah. Okay. Now, likewise, I've mixed these up, but that's okay. That's the weight of the fluid. Excuse me, pushing down on the object. This is the pressure of the fluid pushing up on the object, and that's also related to the weight of the fluid that's below the object, pushing up on the object. But you still calculate that using that height too. So if we think of this height here, that's the weight of this column, rectangle of water above the object, and likewise this height too is the weight of the column of water all the way down here acting on the bottom of the object. Okay, so those are our two pressure equations that ultimately you see those two forces showing up. Now, buoyancy is a force. It says units of newtons, and it's a result of the different pressures acting on the object. So the net pressure, the net force pushing on the object is what we're going to call the buoyancy force. All right, now let's go through this a little bit. So F down is equal to pressure down times area, so I'm just rearranging these equations up here. Okay, solving for F and F up, pressure up times area up. So buoyancy is in the net of these forces, or the difference between those forces. So let's jump over to Newton's laws. If we look at the forces acting on the object, it's equal to the product of mass and acceleration. F equals ma. Nothing's changed here. But as I mentioned, we're going to consider that the object is not moving, has a zero velocity in the vertical direction, and it's constant and zero. Therefore, the acceleration is zero. So this side of the equation goes to zero. So sum of forces acting on the object is zero. Force up plus force down is equal to zero. And I did that right. So force pushing down on the object is negative. Force pushing up on the object is positive. So I've set that up here, and the difference between these two forces is buoyancy. That's not a division sign. That's to represent buoyancy is the net force acting on the object. All right, let's keep going. Let's look at some other math here. We have the buoyancy force is the difference between those two forces. If I substitute the pressure information, because that's what we're looking at, is the result of the pressure pushing on the object from the fluid, I have pressure up times area, and pressure down times area. Just rearranging, A is the same because I'm putting in an object that has the same dimensions. Pressure up minus pressure down. So remember, pressure of the fluid is equal to rho, the density of the fluid, times the acceleration due to the force of gravity, times height of the rectangle of water. We did this in a previous video. All right, so now let's continue this. And now I'm just substituting rho GH for one pressure, rho GH for the other pressure, times the area. So I'm just rearranging here. I have like terms in here, so I have rho GA times H1 minus H2. That represents the difference in depth of water of the height of the top of the top and the height of the bottom. And so the difference between these two will be the height of the object. So H2 minus H1, or I've written it the other way there, that's the height of the object. Okay? So area, remember, is length times width. Therefore, we can reduce this equation to rho GV, or rho G volume. So density of the fluid times the acceleration due to the force of gravity times volume. All right, so now let's go with the equation for buoyancy is density of the fluid times the acceleration due to the force of gravity times volume of the fluid. And if we look at this, what this really represents, because the way our dimensions work out, it represents the weight of the water displaced by the object. It represents the weight of the water displaced by the object. What do I mean by that? Well, if we take that object and we submerge it in the water, it's going to displace the water, or the fluid in this case. It's going to move the fluid. The fluid can't take up the same space. So if we know how much water was displaced, we know the buoyancy force. And so that's what we're actually going to do in another video, is measure the buoyancy force by measuring the weight of the water displaced by the object. Okay, thanks.